The new topic is entitled The Inverse of a Matrix. The inverse of a matrix. And n by n matrix A is called non-singular if there exists a n by n matrix B such that two things happen. A times B is the n by n identity matrix, and B times A is also the n by n identity matrix. A times B and B times A must be the identity matrix. And that's the end of the definition. If there is no such B, if there is no such B, then we say that A is singular. It has no inverse. Okay, I want to say one more thing before this. We call B the inverse of A. Remember, this is where there is a B, so AB is identity. We call B the inverse of A and denote B by A to the negative 1. We read it as A inverse. If there is no B, then we say the matrix A is singular. So non-singular means the inverse exists. Singular means the matrix A has no inverse. It might be possible no matrix has an inverse. It might be the case where every matrix has an inverse. We haven't talked about that yet. Some matrices may have an inverse, some may not. All may not. Suppose A is 3, 5, 1, 2. So matrix B would be 2, negative 5, negative 1, 3. I claim that B is the inverse of A. Okay, I claim B is equals means is the inverse of A. Well, we check. AB, what is it equal? And BA, what is it equal? Well, AB, of course, is A, 3, 5, 1, 2, times B, 2, negative 1, negative 5, and 3. And we get 1, and 0, and 0, and 1, which is the identity matrix. Okay, what's BA? 2, negative 5, negative 1, 3. That's B times A. If you work this out, and I am checking it as we go along, this is 1 and 0 and 0 and 1. Yes, it is I2. So B is They're inverse of A. I mean, forget about this claim for a moment. I showed that AB and BA both equal the identity. We also have that A is the inverse of B. I mean, you may say, but you put A first, so we're talking about that being the inverse of A, and when you switch it around, they still both give you the identity. But wait a minute. Look over here. I wrote B first, and BA equaled identity, and when I switched the A into B, I got the identity. So A is the inverse of B. If A is the inverse of B, then B is the inverse of A. They come hand in hand. They come as a pair. If A is the inverse of B, then B is the inverse of A. If you're a woman and this other woman is your sister, well then your sister can say regarding you, you're my sister. You're sisters. Just like A and B are inverses of one another. They're not sisters, A and B, but they're inverses of one another. Going to prove a very important theorem. Going to show that inverses are unique. Theorem. If A has an inverse, then it's unique. Then this inverse is unique. And generally, the way you prove theorems of this flavor is you suppose there's two inverses and show that they're equal to one another. Proof. Suppose B and C are inverses of A. So BA is the identity matrix and AC is the identity matrix. Okay, if you multiply A on either side by its inverse, you get the identity matrix. If you take A and multiply it by its inverse, C, you should get I. If you take the inverse of A and multiply it by A, you get A. Sorry, you get the identity. Now B is equal to, and I want to show that it equals C. Well, B is equal to B times the identity matrix. Nobody's going to argue that. But the identity matrix, yes, it's BA, but now I'm going to say it's AC. It's AC. And we're multiplying three matrices. Matrix multiplication has their associative property. This is equal to BA times the matrix C. But you know what? BA is identity. So now you have the identity times the matrix C, which is matrix C. That is B equals C. And that's the end of the theorem. B equals C. B equals C. So, in fact, there's only one inverse. Therefore, A has a unique inverse. Turns out that we claimed there's two, but we were wrong. Or at least two, but we were wrong. You may say, but you're right. Well, what if there's more than two? There's three of them. Well, once you show the first two inverses are the same, So now, with respect to the first two, suppose you say B, C, and D are inverses of A. Well, this theorem says that those two are equal to one another. That is, there's only one in that box. There's only one inverse. And if you take this one inverse and the second inverse, oh, you have two inverses, they must be equal. Anytime you have two, they must be equal. As a domino effect, if you have 200 inverses of A, they're really equal. If I tell you B sub 1, B sub 2, B sub 3, all the way up to B sub 200, are all inverses of A, what can you tell me about B1 and B2 and B3, all the way up to B sub 200? The answer should be they're equal. They're all equal to one another. You can't have more than one inverse of A. Okay. Another theorem. If A is non-singular, then A inverse is non-singular. Now, maybe I haven't even mentioned this, but if I have, not enough. For a matrix to have an inverse, it has to be, well, by the definition, I said a matrix A is called non-singular if there exists the matrix B so that AB equals BA. But the key thing I said, or in this time I left it out, if A is an n by n matrix, you can't talk about inverses unless the matrix is a square matrix. If it's not a square matrix, don't even talk about inverses. I will show square matrices that don't have inverses. I've already showed some that do have an inverse. But there are some matrices that has no inverse. Well, no, I want to make a stronger statement here. A is non-singular if and only if A inverse is non-singular. Either they're both non-singular or they're both singular, both being A and A inverse. So let's go this way, to the right. That is, we assume this. Assume A is non-singular. I want to show that A inverse is non-singular. Now, remember, if the product of these two matrices is I, then the inverse of that second matrix is the first matrix. That is, the inverse of the second matrix is the first matrix. Yes, absolutely, the inverse of the first matrix is the second. If a product of two matrices equals to the identity, then we have this down here. A inverse is B, and B inverse is A. So A is non-singular. Well, that implies there exists matrix B such that, well, you know what? We already know what to call it. If A is non-singular, then A inverse exists. In fact, A times A inverse is the identity. Now, don't get caught up with the name of that matrix. If A times B is the identity, then B is the inverse of A. This matrix is the inverse of A. actually, I want to say the other one. Okay, hold on. Let's see. I want to show that A inverse has, okay. I want to show that this matrix has an inverse. The inverse of that matrix is A. Why? Because the product is identity. I was right saying that whatever the second matrix is, I want to say is the inverse of the first. No, that's not what I want to say. I want to say the inverse of that matrix is equal to the left matrix. The inverse of the right matrix, which is denoted this way, is equal to the left matrix. So the inverse of this matrix, which happens to be called A inverse, exists. That is, A inverse is non-singular. If A matrix, whether it's A inverse or Q, if this matrix has an inverse, then that matrix is non-singular. Okay, let me erase this, and then we'll go the other way. Sorry for being a bit sloppy on the proof. I knew it was good. I knew the proof was going to come from those two facts on the bottom. I just didn't know which of the two I was going to use. Okay. Okay, so now we do an if and only if proof, going in the other direction. We assume that A inverse is non-singular. Okay, we want to prove that A inverse is non-singular. Then there exists the inverse of this matrix, which is A, such that A inverse, that matrix, not including inverse, that matrix times its inverse is equal to IN. But everyone will agree with that statement. But that implies A has an inverse. They come in pairs. If A inverse has an inverse which is A, well then A has an inverse which is A inverse. A has an inverse which is A inverse. Therefore, A is non-singular. A has an inverse. So it's non-singular. So if A has an inverse, A inverse has an inverse. If A does not have an inverse, A inverse doesn't have an inverse. In fact, I shouldn't even say that. If A doesn't have an inverse, you can't say A inverse doesn't have an inverse, because A inverse doesn't even exist. But if A has an inverse, then A inverse has an inverse. If A inverse has an inverse, then A has an inverse. They happen hand in hand. Okay, now here's an unusual looking theorem. It reminds me of a product, taking a transpose of a product. Remember, AB transpose you switch to A and B. That is, you have BA, but you transpose each of them. This theorem says if A and B are the right sizes and non-singular, then the inverse of the product is B inverse A inverse. Okay. Now remember, if the inverse of A is B, then A times the inverse of A, which is B, is B times A, or I. A matrix times its inverse should give you I. Okay? AB, so let's check. The matrix AB times the inverse of AB, which is this. I mean, after all, folks, it says the inverse of AB is this. This is supposed to give me the identity. This is AB. Well, that is AB, and we claim that's the inverse of AB. Well, what happens when I multiply them? I should get identity. And I have 4 matrices being multiplied together. I wrote it down in the same order, but I get to move the brackets around. What's inside that brackets is identity. B times B inverse is identity. A times identity times A inverse. Okay, well, this is A times the identity matrix. I guess I didn't need the brackets around identity. But that's A. Inside the brackets is A. Times that with A inverse. And yes, you get the identity. So, the inverse of that matrix, that is AB inverse, is equal to this. Is B inverse A inverse. Let us look at a numerical example of that. I'll write down 2 matrices with their inverses. And then we'll verify this theorem. Again, just verifying this theorem with 2 matrices is not enough. Maybe you were lucky. Maybe you picked the right 2 matrices. I mean, all day long, I can add 2 integers and get an even integer. I can add 2 integers and get an even integer. I can add 13 and 15. I get an even integer. I can do this all day long. Also, therefore, when you add 2 numbers, you get an even number. No, that's not true. 3 plus 7, how about 8? 3 plus 8 is 11. 11's not even. But all day long, I can come up with examples. That's not enough. It's not enough where you show me a million examples where I add 2 numbers and I get an even number. That's not enough. 0 plus 1 is 1. That's not even. The case is closed. Okay, let the eraser catch up, and then I'll put down the 2 matrices plus their inverses. So again, remember that transpose of a product and inverse of a product of 2 matrices, you switch the order, and if you're talking about transpose of a product of A and B, you switch the order of A and B, but each gets transposed. AB, all transpose, becomes B transpose A transpose. Same exact thing with inverses. AB inverse is going to be, switch A into B, B inverse A inverse. Okay. Right. So, see if it's working now. A would be 7231, and A inverse will be 1, -2, -3, 7. I just know that, believe it or not. And B will be 5, 3, 3, 2. And B inverse will be 2, -3, -3, and 5. Okay. So, what is AB? What is AB? Well, A is 7231 times B, which is 5332, and we get 41 and 25, and we get 18 and 11. That's AB. Now, you can verify this, but the inverse of AB is going to be the following. It's going to be 11, -25, -18, 41. It's going to be 451 minus 450. Wonderful. Well, of course it's going to be 1. Okay. Yeah. So that's the inverse. That's AB inverse. Okay? And verify it. Multiply AB, multiply AB. AB, we claim is that. Multiply it by the inverse of AB, which is that. And verify when you multiply those two matrices, you get the identity. But what we want to do is look at B inverse, A inverse. B inverse is 2, -3, -3, and 5. A inverse is on the top left, or this near the top left. It's that matrix. And when you dot this with the first column, you get 2 plus 9, which is, of course, 11. And then when you dot it with the second one, you get -4 minus 21, which is -25. And the second row with the first column gives you -3 minus 15. That's minus 18. And with the last column, you get 6 plus 35, which is 41. And you say, look at that. This guy's right. Okay, it really worked out. Okay, a lot of things you should verify. Verify that A times this matrix is identity. Then I can call it A inverse. Multiply B and B inverse. Make sure you get the identity. Or let me say it differently. Multiply B with this matrix. And then if you get the identity, say, yeah, that is B inverse. Multiply A times B. Get this matrix at the end. Okay? You won't be able to compute AB inverse on your own yet, but do make sure that when you multiply AB with what I'm calling the inverse of AB, you do get the identity. So basically, you are given 1, 2, 3, 4, 5, 6. You are given those 6. Let's pose it that way. You're given that. And you're asked to verify the theorem. So, you take B inverse, multiply it by A inverse, get your answer, and then say, yep, it is AB inverse. They really are one and the same. AB, the inverse of that, is B inverse, A inverse. The order of the inverses gets switched. That's what you need to take with you. The order of the inverses gets switched. So let me hammer that in a little bit better, a little bit more, by looking at like a special case. Now remember, these matrices A and B that you are taking the inverse of, there's nothing special about them. They're just two square matrices of the same size. So if you have AB, and you want to take the inverse, well, you switch the order of the A and the B. Let me say it differently. You switch the order of the two matrices being multiplied, and you inverse each of them. Well, what if, say, the second matrix already was inverse? Well, it's not a problem. You switch the orders of the two matrices, and you inverse each of them. The thing is, B inverse inverse is B. So you get B A inverse. If the first matrix was inverse, but not the second, not a big deal. You switch the order, you have B, A inverse, and then you inverse each of them. But A inverse inverse is A, and B inverse is to the left. Of course, if they were both inverse, it's not a big deal. You switch the two things. Oops, I didn't write inverse. You switch the two, and then you inverse them. B inverse inverse is B. A inverse inverse is A. Okay, so just remember that the A's and the B's, or the two matrices that you're multiplying, that you then want to take the inverse of, any one or both of those two matrices that you are multiplying could have an inverse symbol. And again, those two matrices that you're multiplying and taking the inverse of, they must be non-singular. Again, before you can find the inverse of A and B, which is B inverse A inverse, well, A, you have to be able to find A inverse. That means A has to be invertible or non-singular. B, to find B inverse, B has to be non-singular. You have to be able to calculate the inverse of B. It makes no sense to say that the inverse of AB is B inverse times, there is no A inverse. How do you multiply B inverse by, I don't know what A inverse is. You can't multiply B inverse by, there is no A inverse. Here's a fun theorem. It's just fun. Just gets you to think a little bit. If A is non-singular, then A transpose inverse is A inverse transpose. Okay, it'd have been nice if some of that showed up. What's going on here? The eraser seems to be still erasing. Okay. Sorry about that. If A is non-singular, then A transpose inverse is A inverse transpose. Okay, proof. go by definitions. A is non-singular implies A inverse exists. Now remember, if A is non-singular, then A inverse is non-singular. A inverse exists, and in case we need it, is non-singular. Okay. Now, A transpose inverse. Now remember, we're taking the inverse of what's in the bracket, and we claim it equals that. Well, that would be true if and only if I take A transpose and I multiply it by its inverse. Okay? If I take A transpose and I multiply it by its inverse, I should get the identity. I take A transpose and I multiply it by its inverse, and I'm supposed to get the identity. Okay? That is, this statement is true only if this statement is true. Okay. Now, remember, scratch that. A transpose B transpose is BA transpose. Okay, and the transpose of the identity is just the identity. So, let's look at this. One matrix transpose times another matrix transpose. Well, you can switch the order of the matrices being transposed and transpose that. But wait a minute. That's the identity. Oh, we're going to transpose the identity? Make sure you believe that when you change the rows and the columns of the identity matrix, you get back the identity matrix. Okay, I mean, if you have a 3 by 3 identity matrix, well, if this is the first row, you want that to become the first column. If that's the second row, and it is, you want it to be the second column in the transpose. If that's the third row of a matrix, the transpose would have that as the column. But notice, these are both their identity matrices. They're both I3. And it's going to be true for I4 and I5 and I2. It's always true. The transpose of an identity matrix doesn't change. In fact, the transpose of any scalar matrix doesn't change. Why? Because when you transpose, well, we're talking about square matrices. The transpose of a matrix does not change the location of the entries on the diagonal. Because the diagonal entries are A11 and A22 and A33 and A44, etc. But when you switch the I into J, when you say A44 becomes A44, the entry didn't change. And the entries off the diagonal, like A23, well, when you switch to 2, and A23 is going to be 0, because you're a scalar matrix. And when you switch the 3 into 2 to get, well, what did I first say? A23, which is 0. When you switch the 2 into 3, you get A32. And that's also going to be 0, because anytime you're off the diagonal, the entry is 0 in a scalar matrix. Okay. Now, there's a corollary to the proof that we did earlier. I won't prove it. It's an induction proof. Remember, I said that AB inverse is B inverse A inverse. Well, if you have more than two matrices being multiplied and you want the inverse, that is A1 times A2 up to AR. If you want the inverse of that, well, just write it in reverse order. AR, 1 less than R, all the way down to A2, A1. But you have to take inverse it. If you think about it, this times this should give you the identity. Well, here, that product is going to reduce to identity, and you can remove it. And then the next product is the identity, all the way down to the next to the last product will be identity. And then that will be the identity. That's the gist of the proof. So you don't, the theorem that said AB, all inverse is B inverse, A inverse, that can be made, you can say it in general. Be multiplying not just 2 matrices, but 22 matrices. This corollary said it's not only true for 2 matrices, it's true for any number of matrices. Now here's a nice theorem that gives us another way of showing that 2 matrices are inverses. If I asked you before this theorem to show that B is the inverse of A, you would have to show me that AB is equal to I and BA is also the identity. You'd have to show both of them. But this theorem says no. It says if AB gives you the identity matrix, then BA will give you the identity matrix. That is, from now on, to show that B is the inverse of A is no longer an and in the middle. You don't have to show that AB is identity and BA is the identity. You can show one or the other. You can show this is true or this is true. You don't have to show both anymore. So that's a pretty nice theorem. Okay, well, here's the proof. If AB is equal to IN, and that's what we're allowed to use, if AB equals IN, that means that A is the inverse of B. What's the inverse of that? Since the product is IN, what's the inverse of B? You should say A. A is the inverse of B. A is the inverse of B. Okay. Now, I want to show that BA is also the identity. Well, if I switch these and took their inverses and then took the inverse of that, that will give me BA. Why does this equal BA? Because if I switched it, says inverse, if I switch the two things being multiplied, and then I take the inverse of each, which the inverse of B inverses B, and the inverse of A inverses A, oh, look, I really do get back BA. I really do get back BA. Okay. But remember, B inverse is A. So I'm going to rewrite this, except for B inverse, I'll write A. A inverse times B inverse. Inverse. A inverse times A is identity. And the inverse of the identity is the identity. Remember, I times anything gives you back to anything. Well then, I think of this I as identity. I times that matrix will give me back that matrix, the identity. This is the identity. So we showed that BA is the identity, if AB is. If AB is the identity, then BA is. So from now on, to show that A and B are matrices, to show that A and B are inverses of one another, you can show AB equals the identity, and your classmate can show B times A is identity. You don't have to show both. From now on, it's one or the other. In fact, if AB is not the identity, don't bother showing that BA is. Because it won't be. Because if BA is the identity, well then AB just has to be the identity. Again, we're only talking about square matrices. Now, we're going to go back and talk about elementary row operations. Every elementary row operation can be achieved by matrix multiplication on the left for the record. Suppose you have this matrix A, B, C, D, E, F, G, H, I. One elementary row operation was to interchange two rows. Suppose I want to interchange the first and the second row. Well, if you take the identity matrix and you interchange the first and the second row, and that's what I did, I switched those. If you notice, and please, multiply it out, multiply these two matrices, and notice that the first and second row changed. The first and second row changed. Of course, I didn't really prove that given any matrix, any square matrix, you could interchange row I and row J. I just showed in this 3 by 3, there's a matrix that will switch the first and second row. But it's going to always be true. If you have a 4 by 4 matrix and you want to interchange the second and the fourth, you have 1, 0, 0, 0. The second row of the identity matrix becomes the fourth row. The second row is now going to be the old row 4, and the third row does not change. Okay, I know I didn't say that so carefully, but all I did were interchange row 2 and row 4 of the identity matrix. That will, if you multiply, if you put that on the left of a matrix, you put it on the left of row of matrix A, you will interchange the second and fourth row of matrix A. It's pretty neat. Convince yourself that this works. My showing you is not going to convince you. You need to suffer through it yourself. Now, what if you want to multiply a row by some number, a non-zero number? That was another elementary row operation, being able to multiply a row by any number you want. So I'll put down a 3 by 3 matrix, the same one, A, B, C, D, E, F, G, H, I. And I'll show that you can multiply row 2 by 7. And what you do is you always modify the identity matrix. Instead of, on row 2, instead of having a 1, where you normally have a 1 in the identity matrix, put 7. Just put the number 7. Okay, you don't put 3, you don't put 7 elsewhere, you just put the number 7 right where I said. Okay, just notice what I wrote on the top. It doesn't look so perfect. Okay, so I want to multiply the second row by 7. One zero zero 070 001. This will give me the first row with no change. The second row gets multiplied by 7. If you wanted to multiply by 17 instead, put a 17 on the diagonal entry in row 2. There it is. The next and last one is you want to multiply a multiple of one row and add it to another row. I want to multiply row 1 by 3 and add it to row 3. I want to multiply the first row by 3 and add it to row 3. That is, row 1 is not changing. Row 2 is not going to change. But I want to multiply this by 3 and then add it to the third row. So I'm going to have 3a plus g, 3b plus h, and 3c plus I. And what is the matrix going to look like? Well, like always for these type of problems, you want to modify the identity matrix. In row 3, I want to pick up 3 times row 1. Put a 3 here. And you think about it. When you dot this with the first column, this 3 gets multiplied by the a, which gives us this 3a that I wanted. And 0 times d doesn't add anything. And I add on 1 times g. When I do the first row with the third row with the second column, I get 3 times b plus h, 1 times h. 0 times e won't contribute anything. Same for the third column. Picture that this 3 is multiplying every entry in row 1 by 3. And this 1 is adding on 1 times row 3. Pretty neat stuff. So now we have elementary row operations to reduce. We can use elementary row operations or matrices to reduce a matrix. We can use matrices to reduce the matrix A. Okay, we're going to use matrices to reduce the matrix A to RREF form, which is quite interesting. All right, so let's continue and try to understand what's going on. We want to reduce matrix A to the identity matrix. Okay, so we have A on the left. We perform the first elementary row operation, and then to the left of this, we perform a second one, and to the left of that, we perform a third one. Since the brackets are going to absolutely go crazy, I'm not going to put any. And we keep doing this until we do the last elementary row operation. And what do you know? We get the identity. Okay, we get the identity. Now, remember, matrix multiplication has their associative law. It has associative law. I wrote down the same equation, and I'm going to put the brackets like that. So wait a minute. What's in this bracket, when I multiply it by A, it gives me the identity matrix? Yeah. Oh, that must be A inverse. That must be A inverse. And then you say, is there a nice way of figuring out what ER times, well, I don't want to say it to confuse you even more, but is there a nice way of figuring out what's inside these brackets? The answer is yes. Remember, now we're not going to use we're not going to use matrices anymore. If you have matrix A, you perform some, let's write it down. 1, 7, 2, 1, 0, 4, 1, 1, 1. You perform elementary row operations. For example, you might say row 2 minus row 1 and row 3 minus row 1, and you would perform that. Okay? But now, let's suppose you augmented matrix A with the identity. In other words, suppose you have 1, 7, 2, 1, 0, 4, 1, 1, 1. And you put the identity matrix here. You put their identity matrix here. Okay? So, let me write down over here what we have. We have matrix A augmented with the identity matrix. Now, whatever you do to row 1 for the matrix A, you have to do for the right-hand side. Whatever you do in row 2 to the left of that vertical line, you have to do to the right of the vertical line. Okay, so if you do some operation, some elementary row operation to A, call it row operation 1, well then you end up doing it to the identity. And R1. And then if you do a second operation to R1A, you have to do the same thing to R1I, which is multiplied by R2. And if you keep doing this, well then you're going to get, why am I using R? Well, let's use E for elementary. Let's just use E. So you have E sub R all the way down to E1 times A. And this is augmented with ER all the way down to E1I. Well, I said you wanted to know what this is. Oh, look, it's right here. Oh, look at that. When we multiply it by I, we get this back. That is ER all the way down to E1 times A. That's going to give us ER all the way down to E1. I didn't mean to write equal. Okay. Now, one last thing. One last thing, or maybe 2 lines. This on the bottom is identity. This is the identity. And on the right side, we have ER through E1. But ER through E1 is the inverse. Reduce the matrix A, but don't reduce A augmented with the identity matrix. And then when on the left you reduce A to the identity, what's in the right will be the inverse. If you understood this theory, wonderful. If you didn't, just know that when you take A and augment it with the identity matrix, if you can get it to be row equivalent to the identity matrix on the left, then whatever's on the right, that's A inverse. Whatever it is, it's A inverse. And you really, really should spend time to understand the argument that I just gave. And you shouldn't accept anything in math. But the more you accept, the more shaky you're going to be. You don't know why it's true. If you don't accept it, you prove it, you see it, then you know it's true. It's like, why when you add two odd numbers do you get an odd number? And it's a very simple thing to see. And what it is every odd number is an even number plus 1. 21 is 20 plus 1. 29 is 28 plus 1. And I guess first you'd have to convince yourself that when you add two even numbers, this is true. But why is 29 plus 33 even? Well, 29 is 28 plus 1, and 33 is 32 plus 1. So you basically have 28 plus 32 plus 2. Plus 2. And I'll assume that we agree when you add even numbers, you get an even number. Can you see it? If A and B are odd, well then A is an even number plus 1. And B is possibly a different even number plus 1. And when you add A plus B, you get 2R plus 2S, or 2 times R plus S, plus 2. This is even, and 2 is even. This is even. See? And that's seeing it. If you can see it, you have it. Okay, there's no question about it. It's true. When I see something, I have it for life. Okay? When it comes to math, I know very little math. In fact, of all mathematics, if this represents all mathematics, the most famous living mathematician knows that amount. Knows very, very little of all math. And if I were to blow up that circle, I know that amount. Okay, I know very little math. But whatever I do know, I know well. Why? Because I see it. If you see it, you have it. Okay, so anything your teacher says, anything I say, anything anyone else says about mathematics or any other subject, you should challenge it, like show me why. Why is that true? That makes absolutely no sense to me. Show me that it's true. Okay. So now we have a procedure for finding the inverse of a matrix. Let us find the inverse of this matrix right here. So I take the matrix and I augment it with the identity matrix. And then to the left of the line, I want to get the identity matrix. This number can stay. I want to kill off the 3. So I'm going to triple row 1, which will put a 3 right here. And then I'll just take away row 2. Here is triple row 1. Here is row 2. If I happen to subtract, I will happen to get this. So I have 1, 2, 1, 0, 0, 2, 3, negative 1. Okay? column 1 is done. In row 2, this is my first non-zero entry. So I want to get what's above it to be 0. I'll do row 1 minus row 2. Might be able to just do that in my head. Well, I'll do it underneath. 1, 0, negative 2, 1. 1, 0, negative 2, 1. In the second line, I'll divide by 2 to get my 1 as their leading entry. So basically, to the left, I have the identity matrix, and to the right, I have A inverse. That is, this here is A inverse. That is exactly what A inverse should be. If you took matrix A, and whether you put it on the left or the right, doesn't matter, I multiply these two matrices, and if I am right, I will get the identity. This dotted with that. 1 times negative 2 is negative 2, and 2 times 3 halves is 3. Negative 2 plus 3 is 1. Dot the first row with the second column. 1 times 1 is 1. 2 times negative a half is negative 1. 1 plus negative 1 is 0. Second row, first column. 3 times negative 2 is negative 6, plus 4 times 3 halves. But 4 times 3 halves is 6. 2 times 3 is 6. Negative 6 plus 6 is 0. The third row times the second row, 3, 4, times 1 negative half. 3 times 1 plus 4 times negative a half. 2 goes into 4 2 times. 2 times negative 1 is negative 2. 3 plus negative 2. 3 minus 2 is 1. So here, I did get the identity matrix. Augment the matrix that you want the inverse of with the identity matrix. If you can transform this matrix to the identity matrix, matrix A, the matrix to the left, is invertible. You can find, or is non-singular, you can find the inverse. If, on the other hand, you had a row of zeros, you had zeros for any row to the left of the line, then there's no inverse. The inverse of that original matrix, the matrix that you put over here, it doesn't exist. Okay, if you can reduce the given matrix to the identity matrix, it's not, you can't find an inverse. That given matrix is non-singular. Sorry, is singular. That given matrix is singular. There's no inverse. The theory that I did at the beginning showed that in order to get the inverse, the matrix on the left had to become the identity matrix. Now, I'm not going to prove this, but if you have a 2 by 2 matrix and you want the inverse of it, interchange the entries on that diagonal. The D goes there, the A goes there. Nice and simple. These two, if only you would interchange them, that would make things sweet. You don't have to remember you interchange the main diagonal entries. This diagonal, the minor one, they stay where they are, except you change the sign. If C was negative 7, I put positive 7 there. The sign changes. After all, if you put a negative in front of negative 7, you will get positive 7. Okay. That's not enough. You get 1 over. Now let me just write the matrix down again because I wrote on it a bit. You get 1 over this product, AD, minus that product, BC. Now, regardless of what A, B, C, and D are, this matrix always makes sense. But you are, let me just write it down so we can see this a little bit clearer. You are scaling this matrix by 1 over AD minus BC. This number is not always well defined. And after all, 1 over 0 is indeterminate. Let me spell it better. But nonetheless, it's indeterminate. You can't divide by 0. You cannot divide by 0, whether you want to or not. Indeterminate. That is, AD minus BC cannot be 0. If I call this matrix A, then A inverse is equal to this if AD minus BC is not 0. I mean, after all, if AD minus BC is 0, then A inverse is gibberish. A inverse, to calculate A inverse, you have to divide by 0. You can't divide by 0. So as long as in a 2 by 2 matrix, as long as AD minus BC is not 0, the inverse exists. The inverse exists if AD minus BC is not 0. So, if you have 3, 2, 4, 6, this inverse does not exist since 3 times 4 minus 6 times 2 is 0. 12 minus 12 of 6 times 2. 12 minus 12 is 0. 3 times 4 is 12. 6 times 2 is 12. 12 minus 12 just happens to be the number 0. That matrix is singular. That is, it has no inverse. We tried to find the inverse, but we couldn't. If that product is 0, forget about it. The inverse does not exist. If the subtraction of that product is 0, the inverse does not exist. Now this way of finding the inverse, the shortcut rule, only works for 2 by 2. Okay? If you have 8, 6, 2, 1, and you want to find the inverse, not a big deal. Interchange the 1 and the 8. The 2 and the 6. Just, let's make this negative 2. You change the sign. The negative 2 becomes 2. The 6 becomes negative 6. But then you multiply by 1 over this product, which is 8, minus this product, which is negative 12. That is, it's 1 over 20 times 1, negative 6, 2, 8. Now, if you wanted to check 8, 6, negative 2, 1 times the inverse, 1 over 20, 1, negative 6, 2, 8. You could multiply each of these entries by 1 over 20, get fractions, and then multiply the first matrix by this matrix that has a lot of fractions. Or you could remember that this scalar can come way in front. It's one of the theorems that we have. It's 1 over 20 times 8, 6, negative 2, 1 times 1, negative 6, 2, 8. So first, I'm going to do the two matrix multiplications. Then, and only then, will I multiply by 1 over 20. That is, I better get 20, 0, 0, 20. That way, when I multiply by 1 over 20, I'll get the identity matrix. Okay, this times the first row gives me 8 and 12, which is 20, looking good. When I dot it with the second column, get negative 48 plus 48. The second row gives me 0, negative 2 plus 2. In the last column, the second row with the last column, negative 2 times negative 6 is 12, plus 1 times 8 is 8. 12 plus 8 is 20. Yeah? Remember, multiplying by 1 over 20 is the same as dividing by the reciprocal. Just divide by 20. 20 over 20 is 1. 0 over 20 is 0. Again, 0 over 20 is 0. And 20 over 20 is 1. So here, we got the right inverse. The inverse of 8, 6, negative 2, 1. Honest to God, is this matrix. I know it is. I multiplied the 2 out, and I got the identity matrix. We have a nice, simple way of finding the, if it exists, and finding the inverse of a 2 by 2 matrix. Remember, if that number in front of the matrix is 1 over 0, that matrix, the original matrix, does not have an inverse. It does not have an inverse. Let me do an example. Suppose you have 4, 2, 2, 4, and you want to calculate the inverse. Well, you get 1 over 8. 4 times 2 is 8, minus another 8. Okay. You know, I could have had 8, 1 on the other diagonal. Nonetheless, 8 times 1 is 8. So I have 1 over 0. I switch the 2 and the 4, and the 1 and the 8, the sign changes. But this does not exist. Because what do I multiply each of these 4 entries by? 1 over 0 is, I don't know. What's 2 times? I don't know. What's negative 8 times? I don't know. Or 4 times indeterminate. I don't know how to multiply 4 by a word. I know how to multiply 4 by numbers. 1 over 0 is nonsense. It's a word. It's indeterminate. So the original matrix, 4, 1, 8, 2, this matrix, the inverse of that matrix, boom, 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 does not exist. So when it comes to 2 by 2 matrices, some of them have inverses, some do not have an inverse. So far today, we've seen matrices that have inverses and other square matrices that don't have inverses. Some do, some don't. If you wanted to find the inverse of a bigger size matrix, it's not a big deal. It's not a big deal. Just a lot of arithmetic. If you have 1, 3, 2, 1, 1, 0, and say triple 1, and you want to find the inverse of this matrix, let's call it A. To save space, I'm going to augment it right away. I want to find the inverse of A. And I augment it with the 3 by 3 matrix. If this matrix A is 3 by 3, then the identity is 3 by 3. If the matrix to the left was 3 by 8, you stop right then and there, because you can only take the inverse, possibly, of a square matrix. If it's not square, you're not getting an inverse. I will do row 1 minus row 2 and row 1 minus row 3. The first row, I'm not doing anything to it. The second row, I do 1 minus 1. I do 3 minus 2. Sorry, 3 minus 1, which is 2. 2 minus 0. 1 minus 0. 0 minus 1. And lastly, 0 minus 0. Then I do row 1 minus row 3. 1 minus 1 is 0. 3 minus 1 is 2. 2 minus 1 is 1. 1 minus 0 is 1. 0 minus 0 is 0. And lastly, 0 minus 1 is minus 1. So I have this matrix. And if you were to continue to reduce this, you eventually will get the identity matrix. Okay? I can reduce matrices all day for you, but you need to practice it on your own. If you keep reducing this, you will eventually get this. Negative a half, 1/2, 1, a half, negative 1, 0, negative 1, 1. Okay. This is A, and what's left over here, sorry, of course that's not A, that's the identity, and what's left over in the right is the inverse. A is at the top left, A inverse is at the bottom right, namely here. This here is A inverse. Now, if you wanted to check it, I would factor out a half. A half times negative 1 gives me negative a half. A half times 1 gives me a half. A half times 2 gives me 1. 1, 1. Negative 2 is 0. Negative 2, 2. Okay. So then I could, wish I had a little bit more space. I'll try my best to sneak it in here. I would take the original matrix, 1, 3, 2, 1, 1, 0, 1, 1, 1, and I multiply it by the inverse. But the half can come in the front. The half can come in the front. I'd multiply it by negative 1, 1, 2, 1, 1, negative 2, 0, negative 2, 2. I would multiply those three. That is, these two matrices, and then I would scale it. Don't scale first. In fact, don't multiply A by this matrix. You can, but then you're going to introduce fractions. I pulled the fraction in front. It makes the numbers a lot easier. If you have a 4 by 4 matrix, not a big deal. And you want the inverse, not a big deal. Take that 4 by 4 matrix, augment it with the identity matrix, the 4 by 4 identity matrix, and then reduce so that the left matrix, the one to the left of the line, has the identity matrix. And then what's left over is called the inverse. And then things work out nice and sweetly when you do that. Okay, let us try the next one. It's a theorem that says the following. Won't prove this theorem, but it's a powerful theorem, and you have to know this. And n by n matrix A is non-singular if and only if A and the identity matrix are equivalent. That is, you can reduce the matrix A to the identity matrix. If you can reduce A to the identity matrix, then matrix A has an inverse. It's non-singular. If matrix A is non-singular, it can be reduced to the identity matrix. Okay, that's powerful. You have to know this theorem. The next thing we're going to do is to show how to solve matrices using inverses. Can you solve a matrix using an inverse? Or how do you solve a matrix using an inverse? Suppose we're given the equation. You're given the equation ax equals b. A times x is equal to b. And you're told that A is non-singular. Okay? How would you solve for x? Now, just to remind you, so you're up to speed, if this is A, and you're multiplying it by x, and you want to get b, which is 201. Remember, this is A, this is b, and this is big X. The question is, what is big X? Well, in algebra, if you had 3x is equal to 7, you probably wouldn't, you would divide by 3. But that is the same as multiplying by 3 inverse. 3 inverse is 1/3. You multiply by 3 inverse, and 3 inverse times 3 is 1 times x is x. So the answer is 3 inverse times 7, which is 7/3. We're going to do this similar trick over here. That is, somehow we want to kill off the A. We want to get rid of the A. Well, if on both sides of the equation, on the left, on both sides on the left, we multiply by A inverse. Now, A inverse times A times x, I can multiply in any order that I like. Now, A inverse times A is I. So I times x is A inverse B. And I times x is just x. I times x is just x. So we're done. X is take B and multiply on the left by A inverse. That is, to solve this equation, you can find the inverse of A and then multiply that by B, and you will be done. You will be done. You don't have to use, you can if you want, but you don't have to use Gaussian elimination. You don't have to use Gaussian elimination, Gauss-Jordan reduction. You don't have to use Gauss-Jordan reduction like we've done in the past. For example, if you have the following matrix, following system of equations. Okay, let's wait for our eraser to catch up, please. Sorry for the delay. Okay. Suppose you have this. 3x plus 2y is 5. And I want to have 3y here and 4x here. And this is going to equal 7. Suppose you wanted to solve this system of equations. Writing down the coefficient matrix, we get this right here. We get this right here. This I'll call A. And on the side, I'm going to find out what A inverse is. Well, to find out what A inverse is, you switch these two entries, which is pretty easy because they're the same, and then you change the sign on the other two. The 2 becomes -2, the 4 becomes -4. And then you divide by 1 over 3 times 3, which is 9, minus 4 times 2 is 8. 4 times 2 is 8. 9 minus 8 is 1. And 1 over 1 is just 1. And if you multiply each of those entries in the matrix by 1, you get this. This is the inverse. Okay? So let me just write down the problem because I wrote on it a bit. Okay, there's the problem. If I multiply on the left side by A inverse, if I take this left-hand side of the equal sign and I multiply on the left-hand side by this matrix, and of course I have to do the same on the other side of their equal sign. I take the given matrix, and on the left I multiply by 3, -2, -4, 3. Okay. By design, if this is A, well, that's A inverse. By design, this product is identity. And the identity times xy is just xy. The left-hand side right now is xy. What's the right-hand side? Dot this row with the only column in the other matrix. You get 15 minus 14, or 1. I put that in the 1, 1 position. I take the second row, and I dot it with the first column. And I get -20 plus 21, which is 1. Second row, first column. Oh, that goes right here. Second row, first column. So I'm done. X is 1, Y is 1. Okay, absolutely, you didn't have to write down everything that I'm about to erase. You didn't have to write that down. Well, then what can you write down? You could immediately write down xy equals. You could immediately write down xy equals. And it's going to be the inverse of this matrix times 5, 7. The inverse of that matrix is this. And you multiply it by 5, 7. Which is what we did. And I'll write it down here. And we came up with 1, 1. X is 1. y is also 1. X is 1 and y is 1. 1, 2, 3. But of course, you can only do this if A inverse exists. Now, you're saying, oh, this is so much easier than Gauss-Jordan elimination. Well, I'm not going to argue that. I'm not going to say yes or no. I will say, though, be careful. If you have a 3 by 3 matrix or a 2 by 2 or a 5 by 5 matrix, you spend all this time trying to find the inverse, only to find out it doesn't exist. And then you have to go and use our Gauss-Jordan elimination, or Gauss-Jordan reduction is called. Is you have to be careful. Don't say, oh, this is heaven sent, we're always going to use this, and that's it. No, don't do that. Don't do that. Okay, if you have a 3 by 3 matrix, the inverse may not exist. Like if I asked you to solve 1, 2, 0, 0, 1, 1, 1, 3, 1, well, let's see. 2 and 2. 2 and negative 2. And these are the answers. Negative 2 and negative 1 and negative 3. This is it. X plus 2y, I'm reading the first line. X plus 2y equals negative 2. Y plus z is negative 1. And x plus 3y plus z is negative 3. Suppose you have that. And you say, you know what? I don't like elimination. Well, first of all, you're going to have to find the inverse. So you're going to have to reduce anyways. You're going to have to reduce anyways. That's a negative 2. So if you're given the inverse, like if I told you this is A, and A inverse equals blah, 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 then you can say right away x, y, z is equal to A inverse times B, which is negative 2, negative 1, negative 3. And you'll be done. Okay, now, again, to find A inverse, you would have to do this. 0, 1, 1, 1, 3, 1, 100, 0, 1, 0, 0, 0, 1. You would have to reduce this. You want to get the identity matrix here. Okay? And while you're reducing this, you have 3 columns to reduce. Over here on the left, to solve it using Gauss-Jordan method, you would have to reduce that plus 1 more column. I'd rather reduce 1 extra column than 3 extra columns. And to make matters worse, you might not get the identity matrix. Well, let me come here. You might not get the identity matrix here. That is, it was a waste of time. And you had 3 columns to do. So if you're not given the matrix, unless the problem says on an exam, solve by using inverses, don't solve this problem. Do not solve x plus 2y equals negative 2, or y plus z is equal to negative 1, etc. The third equation, I'll put in a moment. Don't solve this by inverses. Unless you're given the inverse, don't solve by inverse. The only exception would be if on an exam it says, solve by using inverses. Okay, solve by using inverses. Then, please, by all means, use inverses. The teacher said, use inverses. It's not up to you at this point. You have to use inverses. Okay. So if you're given this system of equations, and I'm about to finish up on the very bottom, x plus 3y plus z equals -3. If you're given that system of equations, you should certainly use Gauss-Jordan reduction technique. 3y plus 1z is -3. If you were asked to solve this, you're not given inverse, don't use inverses. Because you may get burnt. When you reduce this, if I didn't make any silly mistakes, you won't get the identity matrix. Okay? It's possible, and please do not hold me to it, because it'll be a miracle if what I'm saying is right. If you reduce this, and you got that, okay, row 1 has a leading entry, row 2 has a leading entry, row 3 does not. For the record, I'll change this, but for the record, this has no solution because the left-hand side equals 0. That is 0x plus 0y plus 0z equals 0 plus 0 plus 0, which is 0. It can't equal 7. So there would be no solution. But I'm going to let it equal 0 now. Okay. Column 1 had a leading 1. Column 2 has a leading 1. Column 3 does not. That means z can be any real number. And x is equal to 3 minus 8z. Minus 8r, because z is r. The second equation tells me y is equal to 5 minus 2z's, minus 2r. Okay? You only get a unique solution when the inverse exists. How about I just call this 0 plus 1r. 0 plus 1r. There are infinitely many solutions. Okay, I'm not proving this, I'm stating it though. If you get just one solution, like x must be 3, 5, and 0. Then, and only then, can you say the inverse of this beginning matrix must have existed. If you get infinitely many solutions, the inverse doesn't exist. The reason is, first of all, remember we're starting with the square matrix. Okay? And the only way you reduce a square matrix and not get the identity matrix here is when you have a row of zeros. Now, if you have a row of zeros and you only have 2 other rows, you can't have 3 leading entries. You can't have a leading entry for row x, y, and z. You can't have a leading entry for 3 columns. If you only have 2 leading ones, well, one of those entries can be in one column, and another one can be in another column. They can't be in this third column because, remember, they have to go down and to the right. So that means that one of the columns won't have a leading 1, which of course means that there'll be a free variable. And once you have a free variable, you have infinitely many solutions. Okay. So that's kind of a theorem. If A is not, if you can't reduce A to the identity matrix, then A either has no solutions because you have a row of zeros and then 5 on the right side, or it'll have infinitely many solutions. There's no in-between there. Now let's talk about homogeneous systems. Okay. Let's remind you that a homogeneous system is AX equals B, except B is 0. It's a 0 vector. Okay, you have 3, 1, 2, or 3x plus 1y minus 2z, x minus y plus z, or 2x plus 3y minus z, and they always equal 0. Homogeneous means each equation equals 0. Why? By definition. Somebody woke up one day and, they had a lot of cloud in the mathematical world, and they said, if it equals 0, we're going to call it homogeneous. It's by definition, nothing to understand. Just one more definition to know. Okay, so now we have this theorem. If A is an n by n matrix, the homogeneous system AX equals B has non-trivial solutions if and only if A is singular. Now, what happened here? Okay, so theorem. If A is an n by n matrix, the homogeneous system AX equals 0 has non-trivial solutions if and only if A is singular. Now, what is this trivial solution? Well, if you have 3x minus y equals 0 and 2x plus 4y equals 0, the key thing here and what I'm about to say is that equals 0. Well, here, of course x equals 0, y equals 0 is a solution. Because 3 times 0 is 0, minus 1 times 0 is 0, 0 minus 0 is 0. Any number times 0, 2 times 0 is 0, plus 4 times 0 is 0. 0 plus 0, yes, it equals 0. 0, x equals 0, y equals 0. If it has 4 variables, if it had 4 equations, 4 unknowns, the 4 variables will all, one solution is the 4 variables equal 0. That will always be a solution. That's the trivial solution. To have non-trivial solution means there are other solutions. Like 3, x is 3, y is 4, z is 9. Okay, it has other solutions, not just 0, 0, 0. Okay, now it might be the case if it has other solutions, then it has infinitely many other solutions. But that's not an issue here. It has non-trivial solutions. So it has other solutions. And it's saying the homogeneous system has non-trivial solutions only if A is singular. Well, let's just say what that means. It says this has non-trivial solutions if and only if this is true. Now, here's some logic. If A, if and only B, you can negate both of these. If you don't have A, then you don't have B. If you don't have B, you don't have A. This is saying that A and B happen at the same exact time. Well, if A doesn't happen, well then B can't happen. That would contradict it. A and B happen at the same time. So I can negate both of them. I can say that is, if AX equals 0 it doesn't have non-trivial solution. That is, it has only the trivial solution, or let me not say if. AX equals 0 has only the trivial solution if and only if A is not singular. That is, A is non-singular. The theorem up here, well, we're assuming that A is an n by n matrix. This theorem right here, AX equals 0 has non-trivial solutions if and only if A is singular, is 100% equivalent to this one. Okay. Now, I'll prove one direction. If I see the other direction fairly easily, I'll prove that as well. But let's suppose A is non-singular. Proof in that direction. Suppose A is non-singular. That means, which implies A inverse exists. That is what it implies. That AX equals 0. We were given that. If I multiply on both sides of the equation, on the left side, not the right side, but on the left side, I multiply by A inverse. Well, A inverse times A is identity, times X is just X, and A inverse, any matrix, times the 0 matrix is the 0 matrix. So yeah, if A is non-singular, X must be 0. So AX equals 0 has only the trivial solution. And now you can try to prove if AX has only the trivial solution, then A is non-singular. You can try proving that. So again, even in solving homogeneous system of equations, you don't want, unless you're given the inverse, you don't want to try to find the inverse because it may not exist. And then you spend all this time to find the inverse and it doesn't exist. And now, let me even go further. Let me go further. I'll show you how it's always more work, even if you do find the inverse. Suppose this is true. I doubt it is. But suppose you have 1, 2, 0, 0, 1, 5, 1, 2, 0. Well, all right, here. You have x plus 2y is equal to 7. And you have y plus 5z is equal to 2. And you have x minus 3y is equal to 11. Suppose you wanted to solve this. Now you have two ways. You could reduce this, and let's just suppose for argument's sake it reduces to this. It reduces to this. 1, 4, 5. Well, this would tell you the answer. X is 1, x is 1, y is 4, and z is 5. And you're done. But now, if you try to do inverses, or if you did do inverses, you would put the identity matrix here. And then you would reduce. And every time you reduce, instead of having one column on the right, you have 3 columns on the right. And nonetheless, you reduce it, you get 1, 0, 0, 0, 1, 0, 0, 0, 1, 7, 1, 2, 3, 1, 4, 0, 0, 4. Okay. But you're not done. You're not done. Now you have to take the inverse. Now you have to take the inverse and multiply it by the right-hand numbers. And then, whatever you get, that will be x, y, z. And when you multiply these two, if I had the right values, you would get what we got earlier, 1, 4, 5. But look at how much extra work you did. You reduce the matrix, and then you're done. X is 1, y is 4, z is 5. But here, if you reduce it to find the inverse, you'll still have the same number of steps that we had on the top. But then you have to take the inverse. First, you have to pray that the inverse exists. You take the inverse, here it is, and then you multiply it by the right-hand side. It's a lot more work to do it that way.